All right, here's a quick introduction and run through of how to solve half-life problems using tables. So our learning target today, understand the concept of radioactive half-life and use it to solve problems relating the amount of a radioactive sample remaining to the amount of time that has passed. Quick review, some isotopes are unstable. An unstable nucleus may emit a particle at any time. Emitting a particle changes the number of protons, thus changing that atom into a different element. So the amount of the original substance decreases over time. This is radioactive decay. So as less and less of the original element remains, the rate of decay slows down. So a graph of the amount remaining over time looks like this. It is a curve that asymptotically approaches zero. A little bit intimidating at first, except we're fortunate that for every element, the time needed to reduce the amount by exactly half is a constant, no matter how much you start with. So the time needed for the amount of an isotope to decrease by exactly 1/2 is called the half-life. Half-life is always the same for samples of a particular isotope, no matter how much or how little you have. Each different isotope has a different half-life. So the plot shows the decay of radioactive carbon-14, which is used in dating fossils and artifacts from the last few thousand years. The half-life of carbon-14 is 5,730 years for a sample that's initially 100 grams. After 5,730 years, 50 grams remain. After another half-life, total of 11,460 years, 25 grams remain. After one more half-life, 17,190 years, 12.5 grams remain, etc. So what are half-life problems? In half-life problems, we're asked to relate the change in amount of a radioactive sample to the amount of time that has passed. We might be told an initial amount in the half-life and asked how much is left after X amount of time. Or we could be asked how long until only Y amount is left. The challenge is keeping straight that time increases linearly, one half-life at a time, while amount changes geometrically, being reduced by a factor of 1/2 for each half-life that passes. In solving problems, organization is half the battle. We organize the information we are given, then we organize our solution one step at a time. For half-life problems, a good strategy is to use a table. Each row of the table represents the passage of one half-life. So we make a table with 4 columns and we have a row for each half-life that goes by. We're going to keep track of 4 things and update what they are at each half-life. The number of half-lives that have passed, the total time that has passed, the fraction of our original sample remaining, and the mass that is still remaining as it decays away. We start with the first row. Always pause here and think, what is the starting point? The starting point is that nothing has happened yet. And this is one of the pitfalls of this approach. Remember, nothing has happened yet. We're at 0. So 0 half-lives have gone by. We put a 0 in the first column. And no time has passed, so we put 0 in the second column. Now, before the sample started to decay, how much is left? All of it. So that's a fraction of 1. And the mass remaining at this point is everything. We'll call it the starting mass. The second row is after 1 half-life, so the number of half-lives is 1. The total time that's gone by is going to be 1 times whatever the half-life is that's given in the problem. Now look at the third column. How much is left? Well, the definition of half-life is that it's the time when exactly half is left, so 1/2 the original sample is left. And the mass is half whatever you started with. Okay, next row, 2 half-lives. Total time is going to be 2 times the half-life. Fraction remaining is going to be half what we had 1 half-life ago, so 1/4. And the mass remaining is going to be half what we had 1 half-life ago, so 1/4 the starting mass. 3 half-lives. Time that has passed is going to be 3 times the half-life. The fraction remaining is going to be half what we had 1 half-life ago, so 1/8. And the mass is going to be 1/8. All right, so let's do a sample problem. A radioactive substance has a half-life of 7 days. A 24-gram sample of this substance is kept undisturbed for 21 days. How much of the original sample remains after this time? If you can look at that and say, wow, 21 is 3 times 7, 3 half-lives have gone by, that's great, but let's still build a table. All right, so remember, we start at 0, time 0, everything remains. 0 half-lives, 0 time, 100% of the sample, that's a fraction of 1, remains, and in the mass column, we're going to put the initial mass we're given, which is 24 grams. All right, after 1 half-life, how much time has gone by? Well, the half-life is 7 days. 1 half-life is 7 days. Fraction remaining, half what we had 1 half-life ago. Mass remaining, half what we had 1 half-life ago, 24. Half of that is 12 grams. All right, after 2 half-lives, how much time has gone by? Another half-life, another 7 days added to the previous 14 days. Fraction is going to be 1/2 what we had a half-life ago. That's a quarter. And the mass is going to be a half of the 12 grams we had 1 half-life ago, so we have 6 grams. Third half-life, total time. All right, this is the trickiest cell in the entire table, and I've circled it in red on the worksheet because you go 7 days, 14 days. You might be thinking, you're going to go to 28 days. No, be very careful. Time goes up by 1 half-life, 1 half-life, 1 half-life. One more half-life after 14 days is 21 days. Okay, fraction remaining is going to be half of what we had 1 half-life ago, or 1/8. And mass remaining is going to be half of what we had 1 half-life ago. Half of 6 is 3 grams. All right, so let's look back at the problem. Now we've got the table filled in and figure out just what is the question we're answering. So the substance is kept undisturbed for 21 days. So we're going to want the bottom row of the column of the table, the one that has 21 days in it. And they want to know how much of the sample remains after this time. That's going to be our 3 grams. All right, so that is a quick walkthrough of how to solve these problems using a table.